So the first one was about cosmology from geometry. Now we'll do cosmology, what constraints we get on cosmology from growth of structure. Okay? And so, oops. So this is closer to the stuff we'll be doing for the rest of the course. Okay? And I've set it up so that we stick with CMB first, and then we do the other aspects of large-scale structure. We will mainly do for the rest of the course the other aspects of large-scale structure, but as we go through, I'll tell you what of the secondary anisotropies what we're developing will be good for. Okay. And so secondary anisotropies means we have the CMB, and then the light is traveling from the CMB to us. And so, there's the dark ages, and then there's the first stars that form, and then there's, eventually the galaxies form, and dark energy starts to dominate, and then there's the present. Okay? This is kind of an interesting plot also here, because, you were asking about the luminosity distance and how far it is. So it's interesting to see progress in the field. Okay, so 10 years ago, the Sloan Sky Survey was about this big. Okay, and that was already revolutionary. Now we've been pushing out, so the dark energy survey is somewhere out here. Sloan 4 is somewhere out here. Dark energy survey is pushing, around here also. And so this is roughly redshift of 1. And redshift of 1, redshift 1.5 is roughly halfway to the last scattering surface. Yeah, so the mapping is not linear in distance. Yeah. Okay. So let's think about the different things that the photons have to deal with as they're coming from the CMB to us. So sometimes it works, sometimes it doesn't. Huh? Okay. So one effect is the ISW effect, the integrated Sachs-Wolf effect. So this one is an effect that has to do with the following. So let's look at the following, and then we'll come back to this picture. So the idea is that as the photon is traveling to us from the CMB, then it's traveling through a universe that is not completely smooth. So if it falls in a potential well, it will gain energy. So it should get a blue shift. And then it will have to come out, and it will spend the energy to come back out. And so it should, gain and spend the same. And so everything should cancel. And so then that photon, the energy is just doing like a random walk, gain, loss, gain, loss, gain, loss, until it reaches us. And whether it just got a gain or just got a loss when it reached us, that's what it has, compared to what it started with. I mean, there's an overall stretching because of the expansion. Okay. But as it's traveling through a potential well, the universe is expanding, and so the potential well is getting stretched. And so the well it fell into is not as deep as the well it has to climb out of. Okay? And so that would say it should gain energy and lose. It should gain energy but not spend as much coming out. So that would be fine, except that the potential well itself might be collapsing and becoming deeper because of that. And so it's possible that the stretching of the potential because of the expansion and the collapse of the potential because of its own gravity, it's possible that they cancel. And so one of the things that we'll do tomorrow, that Anjan will do, he'll do the linear theory calculation of how the potentials evolve in linear theory. And he will find that the evolution because of gravity will be some function of A, and the evolution because of the expansion is A, the stretching because of the expansion. And so if these two cancel, meaning they're the same, then this potential is not evolving, because the evolution is canceling the expansion. And so then the photon will have no plus or minus. Okay, there will be no effect. On the other hand, if the growth because of collapse is slower than the stretching because of expansion, then the photon will gain energy but not spend as much coming out. Okay? And so this effect is a nice one because we think from the geometry of the CMB that the geometry is flat. And we think from the CMB that it's not all matter. Yeah, so because if it was all matter, then the universe would be too young. It cannot be 14 billion years old, right? So it must have gone through the acceleration phase. And so if you are nervous about the supernova and the systematics in measuring expansion, then it's nice to have another argument that says, although the universe is flat, it is not matter. There must be some other component. And it turns out that if the universe is flat and it is matter, then this factor is A. And so then there should be no effect, because A will cancel A. And so if you see an effect, then the idea is, well, we know the universe is flat. If we saw an effect, it cannot be because everything is matter. So that's the reason for the interest in this thing. So what is the signal then? So the signal is that somehow you want to know whether the photon fell in or fell out of a potential well. But you don't see the potential well, you just see the photons. So how can you do the test? How can you do the check? And so the idea is that you have the sky, piece of the sky with the CMB. That same piece of sky, there are some galaxies. You're seeing the CMB behind the galaxies. So this is the galaxy survey, and that's the CMB. And so now you want to know if, where there are more galaxies, the CMB is hotter or colder on average than where there are no galaxies. No, because that tells you that the photons gained or lost energy when they were close to galaxies. And we think that if there are galaxies, that's probably where there's more matter, that's probably where there's a deeper potential well. And so a fair amount of work has gone into looking for this effect, looking to see if near galaxies there's, photons are slightly bluer. Okay. And people have seen an effect, but as often happens in astronomy, the signal you get is 2.5, 3 sigma. And in particle physics, to claim you saw some effect, you need 5 sigma. And so now the question is, can you make this with higher signal to noise? Thanks.
You have to change that.
This guy here, yeah. And so people have seen some signal, but it's not at high enough statistical significance. And it turns out that the significance is hard to improve on because you're really talking about, these are actually quite big scales. They're roughly a few hundred megaparsec scales where the photon falls in and climbs back out. Okay? And if you count how many such scales do we have between us and the CMB, so we made a rough estimate before, no? We said the distance to the CMB should be kind of 14 billion light years, age of universe times speed of light. Okay? Then from Anjan's talk, we know that we should actually be a little bit more careful than that. We should calculate the comoving distance that he defined, which is this funny integral, right? And if you do that integral, then it turns out to equal 2 times c over h divided by roughly omega to the square root of omega. And omega is 0.3. And so this number of c over h is more like, so c over h would be something like 3,000 megaparsecs or 4,000 megaparsecs, actually 14,000 megaparsecs, okay, if you do the co-moving distance. And so, so if I have 300 megaparsec patches and I have 14,000, so say 15,000 megaparsecs, then there are 50 of them. And so the photons are going in and out 50 times. And so I will get an error on this that is something like square root of 50. And it's very difficult to get much better than this, okay? And so because it's such a large-scale effect, there's something that we call cosmic variance, which is how accurately can you measure something given that we have only a finite universe to observe. And this says that it's going to be tough to get a 5 sigma detection of this effect. Nevertheless, so this is showing you the photon gaining and losing energy as it falls in and climbs back out of the potential well, and it's trying to show you the potential well evolving a little bit with time. Okay, but people have looked for the effect because even if, it's possible that we will see an effect that is stronger than expected. And that will again be some indication of new physics. Yeah? So there's active programs to measure this effect. The B? So the dA is the growth factor from linear theory, and that's something that we'll derive tomorrow. Okay? So you'll see, just like we have expansion is some funny function of time, so too the growth factor in linear theory is some funny function of time, and we'll derive that. Okay? And it's a simple function of time, meaning it's proportional to A for Einstein de Sitter, so for matter, omega matter equal 1. Yeah. Yeah, so I said it's roughly 14,000 megaparsecs is the distance to the CMB. And then I said that each one of those potentials is about 300 megaparsecs, something like that. Yeah? And so I said this one is 1,500, 300 is 50. I just divided these numbers. Yeah? But I can, even if I pick 100, so I have 150. So if I take the square root of 150, it's what, 10 or 12? Not 12, but so if I have 100, so square root of 150 is a, so am I messing up the numbers somehow? Yeah, so it would be 120, yeah. And so it's not very many independent pieces, yeah. And then, so this is along one line of sight. I can imagine tiling. So I will get a few, but I will not get a huge number. And to get 5 sigma, I need, tens of thousands. So I'm not going to reach that. Okay.
So your potential is also changing with time, no?
That's right, yeah.
That means it is related to metal density.
That's right. Yeah. Yeah.
But how dense it is, potential would be more.
Okay. So remember, if the potential didn't change, then the photon as it travels will fall into the potential, so it will gain energy. But then it has to come out of the potential to reach you, so it has to spend the same energy. So the net effect will be 0. No? And so then I was saying, so the photon comes, so let's draw. It can be that this is the potential is big, the potential is small, the potential is big, the potential is big, the potential is small, like this. No? So it will be the photon gains energy, loses energy. Loses more energy, gains energy.
That also we assume that while moving inside the potential it spends equal time then while coming up. We assume that? Because it also stretches.
Okay. So first question was if the potential doesn't change. but it's just deep. So that doesn't matter. What matters is if the potential changes. If the potential changes, then you're right. Then you have to worry about whether it spends as long falling in as coming back out. But it's not so much how long as by how much did the potential change between falling in and falling out and climbing out. Yeah? And so for that we need we know that if gravity was not working, then everything is just being stretched. And so then the potential would become, that is what this is trying to show, is that then the potential would just get stretched, and so it would not become so deep.
Yeah.
And then, because in fact gravity is working, it is trying to make the potential deep again. It's trying to fight against the expansion. And so there is one special case in which the growth because of gravity and the decay because of expansion are the same. They cancel. And that case we will derive tomorrow. Yeah? Okay. Yeah.
This 300 megaparsec is the size of this?
Is the rough size of a patch that we, it's also a scale we'll motivate tomorrow for why we should think of 300 megaparsecs as roughly independent patches. But it doesn't much matter if we say 300 or 100. But it's not 10.
So when you say that it's a large scale effect, so like we will have potentials at galactic scale, galaxy bands, cluster scale, and so on.
Yes.
So what particular scale shall we take? What the size of the potential?
Right. So roughly what happens is this argument will also be true if I will just have many more random walks, right? And for the smaller, I actually have a picture that shows you the small scale effect is a more nonlinear effect, and then this one is the linear theory effect, and maybe I should just show you those. Okay, so let's not look at this for now. We'll just look here. So this one is showing you as the photon travels to us, it's gaining and losing energy, it's gaining and losing energy as it climbs in and out of potential. And so it's showing you, as it climbed in and out of the potential for three different boxes. Okay? So that's just to show you the gain and the loss. Okay. Now this was a full simulation, so you can see what's really happening. This is the full effect. This is the piece that I just described, which is only the linear large-scale potentials. And this is the effect from the small-scale potentials. And so the sum of these two is this. Okay? And so sort of what you can see is that, from the linear potential, as you get close to us, that's when you have the large structures, the large pluses and minuses, okay? But sitting on top of these are the lots of small-scale things, okay? So they're there, and if you could resolve it, they're there, but they're smaller effects, okay? They try to show you what it would look like on the map, on the sky, okay? And so this is the full effect on the sky from, so the effect is big from structures near us and not so big from far away. Yeah? So that means that if you were doing this measurement with a galaxy sample that is close to us, then you should see a strong correlation. Whereas if the galaxy sample is far from us, then it's a much weaker signal. Okay? So also the angular size of 300 megaparsecs will be smaller if it is far away from us. And so you can see that the spots are big for sources close to us. And when the sources are further from us, the spots are all factor of 3 smaller. Yeah. So this is the combination of the two. This is the nonlinear only. So you can see that the structures are all much smaller, but you can also see that the amplitude of the effect is smaller. Yeah, so it's a little bit harder to see. This is 10 microkelvin. This is 1 microkelvin. Yeah, so there's an effect, but you need even higher signal to noise to see.
300 is the scale of the potential at some redshift.
At some redshift.
It's different from the 1 degree patch we observe in CMB.
This is very similar to the 1 degree patch we see on the CMB. It's a very similar scale.
But that is at redshift 11 and then this is with varying.
This is with varying redshift.
That is fixed with, this is also fixed with varying redshift.
Yes, so I will derive the 300 megaparsecs for you, okay? So you will see where it comes from. But it's a pretty well-defined scale that we're expecting for that. But remember, for this argument, it's not important that it's 300 or 100. It's important that it's not 1 or 2 megaparsecs, okay? So it's important that these patches, these potential wells in which the photons are falling in and out, more or less, yeah. I mean, again, it doesn't matter too much, right? I can change it and say, because you can see from you can see that more or less these spacings are kind of constant, just the amplitude is smaller here than it was here, okay? There's an interesting reason why the amplitude was smaller here than it was here. And the reason is this. We haven't derived it, so you don't know. But the reason is that this effect was because when the expansion exactly cancels the growth, then there's no effect. And our universe, although today is 0.7, 0.3, it behaves as though it was Einstein de Sitter at early times. Einstein de Sitter is where the growth exactly cancels, and so there's no effect at early times. And then the dark energy starts to switch on, and so now you see the effect. So you see it quite nicely, yeah? So that's in fact why you see the effect here, but not here. But the overall scale is more or less, that's how many patches you have. Yeah? So now we can, if you want, you can say that maybe the potential, the wells are a little bit different size here than here, but it doesn't matter too much because here nothing is happening anyway. It's just the last few. Okay. Okay? All right. Okay. What else happens? So that one was the photons gaining and losing energy. But the photons can be deflected as well. And so that one is gravitational lensing. And so these are the photons being deflected as they travel from the CMB to us. As they're traveling, once again, they're going through these potentials. Okay? And so they're going to get slightly deflected as they travel to us. And we'll use this same kind of idea to make a rough estimate of what we expect of the deflections. Okay? The net results, so I'll show you a couple of simulations, and then we'll go back to an order of magnitude estimate. So if this is the raw CMB with the hot and cold spots, then if the lensing was very strong, then you will see, you see some obvious strange patterns because of the lensing, okay? You can see it's still hard to see, yeah? So it's a small effect, and this is greatly exaggerated to see these big things, okay? And experiments have started to see this effect. Here's a more realistic simulation, okay? Also in the color code of WMAP. So this is unlensed. That's lensed. You see it? I think I matched the size well enough. Okay, so that's not all the shift you're seeing. Okay, so what is happening? So the photons are traveling, they're getting wiggled around a little bit, and so the hot spots, they're getting moved just a little bit. The cold spots are getting moved just a little bit. Okay, and so the amazing thing is we can actually try to detect this. Yeah. So the rule of thumb in today's cosmology is if you can see it by eye, you can detect it with huge statistical significance in data. Okay, and so the rule of thumb is what? So lensing says that basically, so GR says the lensing effect is going to be proportional to the potential, which will be some GM over C squared R. Okay, and so that's the potential. Newton would have been factor of 2, GR is factor of 4 because you get 2 for the spatial and 2 for the time. Yeah. Okay. So that's the order of magnitude, and so we need to know what is the potential strength. And the strength of the lensing potential, well, we see the spots in the CMB, they're 10 to the minus 5. Okay. And we've been through the argument that more or less the potential is going to get stretched by expansion and grow from linear theory, and so more or less it's going to stay constant. At late times it won't be quite right, but at early times this will be quite good. Okay, and so if I multiply this by the 4, I'll get the typical order of magnitude deflection, which is 10 to the minus 4. Okay, and now my photon is coming this way through my blobs that I reach a few hundred megaparsecs. It has to travel this distance, and so there I used 300 megaparsecs. And so again, I'm going to get about 50 of these potentials along the way. Okay, so if I take 10 to the minus 4 times square root of 50, because the deflections are as likely to be left as right? So it's like a random walk. So I have to take root n. Then this is 2 arc minutes. So this many radians is this many arc minutes. And this many arc minutes, for people who are used to thinking in terms of the multipoles, is L of a few thousand. Okay. So 2 arc minutes. So the spots, the typical size of the spots was the size of the moon, and the size of the moon is about 1 degree. No? And so 2 arc minutes is a lot smaller than the size of the spots. And indeed, if it's not like this red spot gets destroyed by the lensing. It's just the shape gets modified slightly. Okay, so this has the following consequence. We think of the CMB as being kind of smooth on the scales on which lensing is moving stuff around. Because lensing is moving a few arc minutes, but the features in the CMB are 30 times bigger. Okay? And so it means that, that you have a hope of detecting this signal itself. So let me show you how. Or let me show you the signal, and then we'll see why this makes sense. So this is that power spectrum of the CMB that I showed you before with, this is telling us the universe is flat. This one is telling us the baryon to total matter fraction. This one is telling us the omega matter. This is telling us the damping. And now you can see with data, we see 7 or 8 of these bumps. So there's a lot of information in here. Yeah. And you can see that around L of 2000, roughly what is happening is that there is more signal than the dashed curve. And the dashed curve is the CMB without lensing. Okay? And so what is happening is that lensing is accounting for this difference. The CMB dropping, that's the statement that the patches are smooth on small angular scales, meaning the patches are 30 degrees and bigger, 30 arc minutes and bigger. So smaller than 30 arc minutes, there are no fluctuations. And that means in these multipoles, smaller than 30 arc minutes is over here. There are no fluctuations. No fluctuations means this is dropping very quickly. And that means this amplitude is all lensing. So that's kind of nice, because that means from the CMB alone, you have a measure of whatever did the lensing, so the mass, the potential wells between us and the CMB. Okay, and so this is a nice measurement because it's using the CMB, but it's telling us something about structure in the matter distribution after the CMB. And so it's kind of a clean probe. Yeah? Okay. Other reasons why it's attractive, we will talk soon about lensing by galaxies, where lensing of galaxies by galaxies. Okay, so there the sources are galaxies, and the galaxies themselves, their shapes are being changed. And that's also another way to do lensing, and was the original way lensing was done. And that's also fine. The difference is that when we do normal galaxy lensing, the galaxies that whose image is coming to you and gets changed, they can be at many different redshifts. And the lensing, how much their shape gets changed, will depend on how much the distance their photons had to travel to us. So with the CMB, the source is at a known distance, 14,000 megaparsecs, co-moving megaparsec, right? So all the sources are fixed. It's one plane that is being lensed. So it's a much simpler problem. Yeah? And in addition, that one source is, the statistics are Gaussian. We'll work out tomorrow statistics of Gaussian random fields, which means we know quite a lot about the distribution of hot and cold spots of the CMB that will then be getting lensed to produce this. Yeah, so it's a very nice controlled experiment of the lensing. Yeah? And so this is definitely a growth field, right? So the first detection was 5 years ago. And things are only going to get better. They're not going to get arbitrarily better because other crap starts to happen. Okay, so now we'll go through what starts to happen. Yeah? So it's not just lensing that matters, but it's a beautiful thing that you can do just from the CMB. Okay. Okay, so the other stuff that starts to happen go under the name of the Sunyaev-Zeldovich effect. And the SZ effect is, someone mentioned it earlier today, right? We have photons from the CMB that are traveling and they hit a big clump of gas. And the clump of gas has electrons. If those electrons are moving fast, then the photons, they gain energy by colliding with the electrons. Okay, so inverse Compton scattering. We know the temperature of the photons because we know they start out at 3 degrees Kelvin, at 3000 degrees Kelvin. They are 3 degrees Kelvin by the present. So along the way, they're something like 30 degrees Kelvin. We think that the X-ray clusters with these things are 1,000,000 degrees Kelvin. And so the photons are really getting kicked. Okay? So it's potentially a very nice effect. It's just that the clusters are rare. Okay, okay, what's the effect? So the effect is to change what was a black body spectrum to something else, because the photons are getting energy from the electrons. Okay, so the crude statement is that the effect is going to depend on how many electrons there are and what the temperature of the electrons is. And so density of electrons, temperature of electrons. So pressure is density times temperature. So it's the pressure of the gas. And so this effect cares about the pressure of the gas. Okay. All right. Next question is, so we're expecting the photons to gain energy, but what sets this shape? Okay. And so I have a little bit in here about how to do that calculation. come and talk to me afterwards about doing it because there are other things I want to cover. I want to just give you a nice way to think of this problem, okay? And the nice way to think of the Compton scattering problem is, so this is doing it as Compton scattering, is this, is that instead of thinking of what you see, think what each electron there saw, okay? So each electron there is seeing a CMB, okay? So it's seeing CMB photons arriving towards it, except the electron is moving. Yeah, because it's in a hot cluster, the cluster has pressure, so it's moving quite fast. So if the electron is moving this way, then it will see all the photons to have higher temperature in this direction and lower temperature in that direction. So it will see a blue shifted or a red shifted CMB, okay? And so each of these photons sees a Doppler shifted black body spectrum because of its motion, okay? And so it reacts as though it sees the gas with a mix of electrons having a mix of speeds is behaving as though there is a mix of black bodies with different temperatures. The distribution of electron velocities becomes the distribution of Doppler shifted velocities or Doppler shifted temperatures of those black bodies.
That?
Yes, okay?
Like
So
mathematically.
So I'll do that in a second, okay? And so the way to think of this is that the net result will be a superposition of black bodies with the range of temperatures given by the range of speeds, so the temperature of that gas, right? So let's do that. So forget about the top part, but let's take the bottom part. So the number of photons that had some temperature, so photons with some wavelength we translate to temperature, right? So we have a Planck spectrum, and now we'll get T plus some delta T. Okay? And so this is the Planck spectrum. So let's do a Taylor series of this guy. Okay, so we'll do a Taylor series of this functional form. So I will get the Planck spectrum, and then I will get, the first order Taylor and the second and the third. Okay? But each time I do that, I will be getting, because I have a delta T, there's the T sitting here, right? So there was really a e to the h nu over k T plus delta T. And so when I take this Taylor series, I will get terms which have delta T's. So now the delta T can be towards you or away from you. And so I have to take a statistical average. That is the thing that is fluctuating. So the terms that are delta T, they average out to 0. But the terms that are delta T squared, they will survive. And so you have to do the Taylor series, and you keep the terms that are delta T squared. Okay?
This is averaging over the patches.
This is averaging over the electrons in one patch. Yeah? And so if you do that, then then you will get a bunch of terms. Okay? And then the rest is just rearranging, because some of these terms, so this guy will effectively look like something with just a shifted temperature, and then there will be genuinely something with that is just proportional to the fluctuations. Okay? So there's just some grouping of terms once you've done this. But the nice thing about this formulation is that in this formulation, everything is just the Doppler shifts. In this case, you just took an average over the pluses and the minuses. But now you can ask, this cloud of gas, it can be that this whole cloud of gas was moving in one direction. Like the cluster had some velocity. And so that will be a term where I don't have to worry about an averaging. There will be a net effect because everything is moving in one direction. And sitting on top of this will be this noise. Okay? This noise is called the thermal effect. The bulk motion is called the kinetic effect. once upon a time, they were derived in two different ways. But there's a very nice derivation that goes back to Landau, Lifshitz, but not in this kind of language. But there's a guy now at TIFR, Khatri. He did some nice work deriving it in this language. Yeah? Okay, so so that means there's a sort of a known shape for the distortion, which comes from just taking this distribution of speeds, okay, for the thermal SC effect. And so I have the algebra here, but let's not worry about the algebra. Okay, let's go and see what should happen. So what should happen is, let me go back a couple of slides. So the net effect is that this shape can actually be calculated. Okay. And what has the shape done? It has taken photons from long wavelengths and made them into short wavelengths. But there is one wavelength at which there was no change in the number of photons. Okay? And so what does it mean? It means that if you look at a patch of the sky for the CMB photons, so cosmic microwave background, so you're looking at microwaves. Yeah? You're looking at, so these are the different frequencies, okay? And as you look at the different frequencies, you see a different signal. Yeah? You see hot at short wavelengths and a hole at long wavelengths, because they're missing from here and there are extra here. Okay, so that's because of this effect, right? So you see it in the map directly as a hole at some frequencies and an excess at higher frequencies. And that means that it's very difficult to confuse it for some other effect. Okay? So if you see this happen, then you know there was a ball of hot gas between you and the CMB at that position in the sky. Now, the angular size of this position is quite small, maybe an arc-minute. Okay? And so it's off order the size of the lensing. Okay? Maybe a little bit smaller than that. But it is smaller than a typical CMB spot, which is 30 arc-minutes. Yeah? Or a degree, something like that. And so that's why you can kind of see this is pretty smooth with a hole in it. So the background CMB is kind of smooth because the clusters are small compared to compared to a CMB spot. Okay. Okay. And so yeah, so this is just an animation showing you what that cluster looks like, right? As you sweep through frequencies. Okay. And okay, so let's look at this. And so now there are projects that are finding hundreds of these. Yeah? So the South Pole Telescope is the main factory for finding these at the moment. But this is the next thing people are doing, right? Okay, so why is it? Other reasons why it's nice. Other reasons it's nice are, supposing I wanted to look at this cluster because of the light that it made, then if it's far from me, it will be harder to see. In this case, I'm seeing it because of the light it changed, right? So the hole that it produces, or the excess that it produces of CMB wavelength photons, doesn't depend on the distance from me. The angular size of it might a little bit, but otherwise the chance to detect it will not depend on its distance. And that's very unusual in cosmology, right? For most things, the things that are far from us are harder to see. And so this is why it's a very popular way for looking for clusters. Yeah? Because to first order, distance doesn't matter. Okay. Okay, so this is spelling out that basically that you can see things independent of redshift. Yeah.
So you get a net change in the temperature. So how do you determine how do you separate the kinetic effect and the thermal?
Good question, right? So I said there are two effects happening at the same time, right? And so one way is to say, because we've gone through the calculation, we know precisely the wavelength at which it crosses 0. Okay? And so that means that at this wavelength, there is no thermal effect. And so if you watch when it hits here, you will just see the smooth CMB. Okay? And so that means that this is where you should look for the KSZ effect. Okay? Now, if I were to draw what I expect for the amplitude of the KSZ effect here, then we haven't done this yet, but we will derive this. I said the typical cluster temperature is 1,000,000 degrees, something like that. Okay? So the typical speeds are pretty huge, 1,000 kilometers per second. Okay? The bulk motion of a cluster is smaller, few hundred kilometers per second. And so the Doppler shift that you get from that is smaller. And so the signal is a lot smaller for the KSZ effect than the thermal effect. And so not only do you have to look in the 0, you have to be that much more sensitive because it's a harder measurement to make. Okay? And so there's been some excitement recently for looking for this effect as well, because it too has been seen, but not directly yet. Okay, so this one is showing you the crude effect is, the photon comes from the CMB, hits the cluster was moving towards you, so you get a net blue shift. This cluster was moving away from you, so you got a net red shift from the KSZ effect. Okay, that effect is a small effect. Instead, people did a clever thing. They said, let me take a pair of clusters. This pair of clusters, they're probably moving towards each other. And so that means that probably this guy is going this way and this guy is going this way. And so I expect the SZ effect to be due to this velocity. And so if I sit on a cluster and I measure the SZ effect, or I measure the temperature at another cluster, then it is encoding this pairwise velocity information. And so I can pull out the KSZ effect from knowing this. So now you're measuring it not object by object, but pair by pair. Okay, and that's the method that is used currently. One day we will do it with individual objects. But currently the technique is the pairwise velocities. It's a nice idea. Yeah? Okay, so not so much with the KSZ effect, but with the thermal effect, people thought this is a nice way to find clusters. And as I'll go on to say, people were interested in clusters because they think clusters will tell them something about cosmology. What people are beginning to realize is that what they can tell you about cosmology, it's maybe interesting, but they tell you a lot about the gas. And that's almost more interesting. Okay? In particular, we know how many baryons there should be from the CMB. We know how many baryons we see in stars locally. So we can add them up. Then we know that there are baryons sitting in X-ray clusters. We can add those up. When we add up all the baryons that we can see, we are missing about 1/3. Now, we think that probably as you go further outside a cluster, maybe there are baryons there, it's just they were below sensitivity, we couldn't see them. Others think, between the clusters, actually there's some filaments, and around the filaments is some gas that is not hot enough to create X-rays, so you didn't see it in X-rays. You don't see it in optical, and so it was hard to find. But with the SZ effect, one of the things you can do is you can you can take these pairs, and so suppose I have a map of the sky, and I have, so I have some clusters here, clusters like this. I can take all pairs that are separated by 10 megaparsecs. Okay, so I can take these pairs. Then I can take these pairs that were here, I can put them on top. So I can make a stack of all pairs separated by 10 megaparsecs. And then I can stack the CMB that was between them. And I can look in that stacked image if the CMB shows an SZ effect. For an individual filament, between these two, that filament was too weak to produce any signal. But if I stack 1,000 of these, maybe I see something. And people are beginning to see it. Yeah? And so those would be the missing baryons. Yeah? And so there's quite a lot of excitement in finding the baryons. For the individual clusters, there is excitement because we will do this kind of on the last day, but in the middle of each of these clusters, we think there was a black hole, but a supermassive black hole, a billion times the mass of the sun. There was the quasar activity, okay? So all that activity heated gas up. If it heated gas up, it changed the pressure. And so you can learn about the processes happening in the center by how the gas around it was heated. This is called feedback in galaxy formation. And so this is a nice probe of feedback. And this kind of study is in between two fields, in between the cosmology guys who are looking for the clusters and the galaxy formation guys who are interested in feedback. So it's kind of open field, it's young, it's not very crowded. And so there's some neat projects that are possible in this kind of study. Yeah? Okay, so this is the SZ effect. Different things that you can do just by stacking in clever ways, yeah, to look for missing gas or gas profiles and stuff like that. Yeah.
This is the scenario power spectrum.
Yes, then they can also measure the power spectrum of this. Yeah, so I haven't shown that, but the power spectrum will give power also on the scales where the lensing is starting to dominate, the SC effect starts to kick in. Yeah, so the lensing is being done by slightly larger scale structures than the individual clusters that are doing the SC, and so the individual clusters are a little bit smaller, but they start to matter.
It can also give clue for dark matter.
Sorry?
It can also give some clue for dark matter.
Yes. So some people are interested in whether dark matter is self-interacting. If there are, in the centers of clusters, collisions may be more, and that can heat not just the dark matter, but also the gas, and that will modify the profile. Absolutely. Absolutely. Yeah. Okay?
Just previous, okay, you're taking the average of del T as 0, okay, the odd powers of it. So that is only possible for the thermal motion, not for the kinetic motion.
Right. So for the kinetic motion, there will be the leading order term that you don't throw away, because there will be a bulk motion term. Okay. So this was looking in the SZ. So looking at the hot gas, but you can also look in X-rays. Okay. And so these are different satellites doing these experiments or doing these observations. And so the crude statement is the following. The lensing is measuring the mass of a lens. The Sunyaev-Zeldovich effect is measuring the pressure. And the X-ray is measuring the temperature. Okay. And so you're getting different estimates of the gas. Another way to think of this is the X-rays are coming from collisions. So that is something like an density squared. So density squared means you upweight the center of the cluster a lot, where the density is highest. The pressure is density times temperature, so 1 power of density. So that's a smoother thing. And so it's as though you are measuring the cluster, but you're not weighting the center of the cluster so much. So X-rays, they measure the center. This guy measures a little further out. And then the mass is the total mass, right, all the way out. And so it's like probing clusters on different scales from different observables. It's also an attractive thing to do. Each one of these has different systematics, so it's nice to put them together. Okay. All right. One other thing that's interesting about clusters is, so this is the famous kind of thing. You've seen the bullet cluster before? Yeah? No? Okay, so bullet cluster. So it's called a bullet cluster because what is supposed to have happened here is you had 2 clouds of gas with their dark matter, and they collided with each other. So when they collide with each other, what happens? Okay. So the leading model, so the leading model of our universe is that you have baryons, but you also have dark matter. The baryons, it's gas. When gas collides, you make a shock. And so when gas collides, then the gas will stay at where the collision happened. But when the dark matter collides, the dark matter, the leading models are that it is a collisionless particle. They are weakly interacting particles, weakly interacting even with themselves, which means to leading approximation, they are collisionless, which means that you should think of a cluster as, you know, in the US, when the basketball team wins or something like that, then they take the bucket of water with ice and they throw it on the coach. Yeah? So the water is the baryons, and the ice are the collisionless particles. I mean, the ice is what hurts the guy, but okay, let's pretend that they're collisionless, okay? So what's the idea? The idea is that when you throw water and ice against water and ice, the water hits, and the ice keeps going, because the ice is like bullets, and if there's few of them, the bullets don't hit each other, okay? So that's what's supposed to happen here, yeah? It's the same idea. If you take a galaxy with another galaxy, and you slam the 2 galaxies together, what happens to the stars? Nothing, right? Maybe tidal streams, but no collisions, right? Because a galaxy, so the sun is if the sun is a basketball here, then the nearest star to the sun is a basketball in Bombay, right? And so I can have 2 basketballs, and I can double the number of basketballs, and it's not going to have a collision, right? So same thing here. The dark matter is supposed to be collisionless, and so if it's collisionless, it passes straight through. And so you can say, well, that's the gas, that's the dark matter, and then you can, so you can look for where the stars are. That's the yellow stuff in the background, because the stars that make the galaxies are also collisionless, and so they've gone through. And so you see this in X-rays. You see this from the gravitational lensing. You infer there must be mass here, there must be mass here. And you can see directly that the galaxies are here and the galaxies are here and not so much in the middle. Okay? And so this is an argument for the fact that there must be dark matter. The dark matter must, to good approximation, be collisionless, whereas the baryons are collisional. Okay? But these are rare things. There are 10 of them on the sky that have been found so far. Yeah? Because the collision had to be just right, aligned just so that you could see it. Now, if the collision happened like this and you're watching, then you can't tell. No, so it was important that the collision was like this. Okay. So that's one nice reason to do individual weird clusters, but it's interesting to do a population of clusters. So why? And so the clusters are the places in the universe where gravity has won against the expansion. So we will quantify how clusters form in the next couple of lectures. But the idea is that if we know gravity, then we can constrain the expansion by counting how often gravity won. That's the crude idea, okay? Then we will refine the idea and say, what if we don't know gravity? Maybe there are alternatives to GR, then what? So we will come back to that question too. But for now, if we know gravity, if it's GR, then we can, from counting where gravity has won against expansion, we can learn about the expansion. So we can constrain expansion history, okay? But in fact, the observations that you make are always, you look in the sky, and you look in a piece of sky, and so you saw clusters out to some distance. And so you saw, you know, clusters from 0 to redshift 0.6. This is a recent survey. And you can see, you know, there's galaxies all over the place, and then they've circled where the X-ray clusters are, and, you know, stuff like this. So redshift means co-moving distance, but co-moving distance means I have to know cosmology. So the volume in this cone is determined by cosmology. So if I count how many clusters are inside this cone, then it's a combination of how often gravity won and what's the volume of the cone because of background geometry, right? And so it's a combination of the geometry and the growth of structure that is constraining the cosmology, okay? Right, so that's trying to put it. No, there will be some number density of clusters. They might have different masses. You just add up all the masses that you can see in some volume, okay? And so that's the co-moving volume. That depends on cosmology. So cosmology enters here, and whether a cluster could pull itself together against the expansion enters here, okay? Okay, there's some details. We'll come back to the details later.
And is the electron density profile?
Yes. So then, so this is written, oh, we need to know the mass of the cluster, but in practice, you don't know the mass of the cluster. You maybe only have the X-ray observations, so you need to know how you convert from the X-ray temperature or the X-ray luminosity or the optical luminosity or the SZ signal to mass. So there's some complicated mapping from the observable to the mass, right? So that is part and parcel of how this is done. And we may have time to go through some of this when we do clusters. Okay. Oh, I didn't plug in. Am I in time? Yeah. So the last thing about clusters is that if we run a simulation of how structure formed, and we change the background geometry, so we change the expansion history, then the amount of structure which forms depends on that background geometry, okay? And so to illustrate that, let's look at just the top two panels, okay? So the top one is what we think is the correct model. So lambda CDM, 0.3, 0.7. This is at redshift 3, redshift 1, and redshift 0. So you can see the big holes here, and they were not so big in the past. This is Einstein de Sitter. In Einstein de Sitter, they've set the model up to look kind of similar at redshift 0. But at redshift 3, they're very different, okay? And so that's a little bit because what's happening in lambda CDM is universe is, and we will work this out in detail tomorrow, but the universe is expanding rapidly today, which means gravity can't do anything today. It's all done. And that means that today looks much like it did in the past, in the recent past. So if you made structures today, they were actually made sometime earlier. Nothing new can be made. Whereas in Einstein de Sitter, the matter is winning all the time. And so that means that the structures you see today were formed recently, which means in the past they were not there. Okay? And so that means that the real test of the growth of structure is not whether the universe looks like this or like this. The real test is the comparison of today with the past. It's the evolution that is the real test of cosmology. Okay? And so...
Why the fourth are defined for z equal to 0?
Sorry, say again?
The four patches are why defined for z equal to 0 for the four pieces.
So why are these also defined?
No, not Z equal to 1 or Z equal to 0, but Z equal to 0, the present hour.
Yeah.
They are defined.
Why are they different? So they did not choose, so we will come to this when we define how it is that you run a simulation to look like the present universe, and so you have to set the amplitude of fluctuation. So there's a bunch of stuff that goes in. Yeah? And so it can be that they didn't normalize them to be all exactly the same at redshift 0.
Sigma 8 to be as
Correct, yeah.
for all.
That's right, and I'm not quite sure that they did that here because they're having to do.
Choose a different power spectrum and normalize that
Correct.
again to the same sigma 8.
Yeah, they're having to play games with normalizing the sigma 8 and thinking what would have been galaxies. So it's a little bit complicated. But the basic point is not whether they agree here. The basic point is that redshift 1 and 0 are similar here but are different here. Yeah, that's the main point. Okay. And why does that matter? So this is data now. Okay, so this is the number density of clusters as a function of their mass. This was taken from an X-ray survey. So there was some conversion that went from the X-ray luminosity to an estimate of the mass of the cluster. Okay, and so they had of order 100 clusters, and that's the shape, okay, of the number of clusters. But at high redshift, there are fewer clusters. Okay, so let's think a little bit about this now. The curve through here is a prediction for some cosmology, and we'll make these predictions, right? So by the end of this week, you will be making these predictions, and you will be fitting this data, okay? But right now, you have a prediction like this. Now, supposing they screwed up. Supposing there are some measurement errors or something like this, and so the correct answer should be here, and all of this is just errors. Okay, they have some systematic error. Then that will change the cosmology that you think is the right cosmology. But if you're comparing two different redshifts, and you have the same systematic that is working at those two redshifts, the comparison of the two is not going to be as wrong as an individual redshift. Okay, and so most cluster catalogs, they are careful now about this to make the comparison using the evolution, not one's fixed redshift, for this reason. It's very difficult to be sure that you have calibrated the masses well. But you can be pretty sure that if you've got it wrong at one redshift, you got it wrong in the same way at another redshift. So, okay. Okay, so that was clusters. We don't have to find the clusters. We can just look at the galaxies. And so this is showing you as time has gone on, the surveys have got bigger and bigger and bigger. And so this was the sort of point I made before, right? That we can go to very large distances, about halfway to the CMB, okay, for the next generation of surveys. And one of the things we see is, galaxies are clustered. This is always a wedge on the sky. And galaxies have a range of luminosities. Some are luminous, some are faint. I'm nearly done. Yeah? And they have different colors. Some are red, some are blue. Okay, but you can see, that the red guys, they all sit together, and the blue guys, they sit where the red guys are not. Okay, and so if your goal is to use the distribution of the galaxies to tell you something about the geometry of the universe, you might get two different answers depending on whether you used red or blue. And so what you really need is some kind of language that lets you translate between the distribution of the light that you see and the distribution of the dark matter that it's supposed to be tracing. Yeah? And so one of the things that we will be setting up is a language to describe this bias between the distribution of the light and the distribution of the mass. Okay. And so that language is the language of the halo model, yeah, that we'll be setting up the last few days of the course. Okay, so we want to describe different point processes which are all from the same underlying dark matter density field. Okay. The halo model. We'll do a few other things. Okay. We will measure the clustering of galaxies on very large scales. These are called Baryon acoustic oscillations. These are things that are based on the same physics as the CMB, just now with galaxies. So this we'll do tomorrow or on Wednesday. Okay. And this one I hope to give you the data for, and so those of you who want to play with it, you can plot it and fit models to it and play around a little bit with this stuff. The baryons are baryons, so it does not matter whether they are in galaxies or in gas along the line of sight between us and a quasar. And so there is every little cloud of hydrogen gas is producing an absorption line, that's telling us about the matter between the quasar and us. And so the clustering of the lines, the clumpiness of the lines is telling us about the clumpiness of the baryons. And we can compare the clumpiness of the baryons to the clumpiness of the galaxies. Okay? And it's a beautiful thing that we will see we get the same answer from doing both. Okay? All right. Oh, one other thing is, if we see clumpy gas in the early universe at redshifts of 3 or so, then it turns out that you can put a constraint on neutrino masses. And so one of the things we will work through is whether neutrinos, structure formation in a universe with neutrinos proceeds differently from one without. And because neutrinos move fast, whereas cold dark matter is cold because it doesn't move far, there's a big effect. And it's a very big effect at high redshift. Right? So this is one way to make that constraint. Final thing we do cosmology with is gravitational lensing. So instead of doing lensing of the CMB now, we are doing lensing of galaxies behind the cluster, and you can see these arc-like shapes. And so those are images of one galaxy in the background that got lensed. Yeah? And so from the instance of strong lensing or of weak lensing, so let me go through fast because I'm late. We've seen maps like this. Background galaxies, their shapes get bent and distorted so that they line up with the large-scale structure. And so by measuring if the shapes are oriented random or if the shapes are somehow correlated with the large-scale structure, we get an estimate of the amount of mass between us and the source of the shape, the light. Not all galaxies have the same shape. And so it's hard to just use the shape distribution. It's much more the alignments of the shapes that is the real lensing signal. That's why the CMB was so nice. With the CMB, it's the hotspots in the CMB. Statistically, we know the shape distribution, no big deal. With galaxies, they can have all sorts of different shapes, so we can't use the shape information. We can only use the correlations between the shapes to tell us information. Okay? The strong lensing is saying, the images get very strongly distorted if there's a big massive thing between the source and us. But far away from the source, there is still a little bit of lensing happening. Far away from the lens, there's still a little bit of distortion. The little bit is hard to see, impossible to see by eye, but if you have 100 galaxies in a shell around, then you can measure a 1% effect. Well, if you have 100 galaxies, you can measure a 10% effect. Okay, so if you want a 1% effect, you need 10,000 objects. Okay, so that's the lensing. And the final one is redshift space distortions that we can describe. So this one is, we never make observations in real space. We always make observations in the line of sight redshift. And so this is dialing up and down the speeds of galaxies. And so you should imagine that we are at the center, and we're looking out. And so if the speeds are high, then we see lots of stripiness along the line of sight. And if the speeds are small, then we won't see that. And so that means the redshift space distortions, the amount of stripiness in the maps, the amount of, in this case, anisotropy, because the clustering along the line of sight to you is different from the clustering across the line of sight. There's clearly a preferred direction. This anisotropy is something that we can measure and encodes information about how quickly things are moving. Things are moving because of gravity, so you're making a constraint on gravity. This is the leading way in which people hope to constrain modifications to gravity, modifications to GR, yeah, is by this kind of data. And so what we will do in the next couple of days is work out that there's really two different types of redshift space distortion, just like with the ISW effect, just like with the lensing. There's the large-scale linear stuff, and then there's the smaller-scale nonlinear stuff. And we'll work through models for both of those, and we'll put them together and put them all together into the Halo model so that you will have the unified language to describe this, the lensing, the BAO, and the clusters all in the same framework. Yeah? So that's the goal. And I should stop there. Yeah? So let me skip to there. So those are the things we've covered, right? Supernovae and CMB for geometry. We haven't done the oscillations in detail, but these are the things we'll be paying attention to in the next few days. All right? There we go.